Hey guys, welcome to the discussion in real analysis with Akhilesh Kumar. In this series, we are discussing on topics of the book Principles of Mathematical Analysis by Walter Rudin. The target of this video is to understand fundamentals of differentiation of functions of several variables in most general sense. All right, because if when we discuss differentiation, in our mind comes the concept of a function f from r to r and f from an open interval to r, and in that case we discuss about the differentiation at a point in the domain open interval as means the rate of change of the codomain points with respect to the domain point, rate of change in domain points. So in that sense, we discuss the differentiation for a function from R to R. But when the discussion comes for the functions of several variables, what all types it can take, let us understand today about that. I'll talk about most fundamental and preliminary facts first, and then we will go to the most general sense of differentiation of functions of several variables. Now, I am considering one generalization of differentiation when first we consider a function from R to R or a subset of R to R. After that means the next generalization what we learn, which generally students learn as partial derivative, etc., or directional derivative. It comes from a function which is from Rn to R or a subset of Rn to R, and then we have a point in the domain x as x1 up to xn belonging to E or Rn, means domain set, and therefore it has components x1 up to xn. In that case, this fx belongs to R because we are considering function f from Rn to R. So domain points are having n components, n variables, or and over that the function image has only one real value. So in that case, what we say the function it as multivariate function. So we will have x1, x2 up to xn, and these are independent variables, and there is one dependent variable y. When then we can write y equal to function of x1 up to xn. So the interpretation of writing this function is a function from a subset of Euclidean space to R1, general R. In that case, we can discuss about partial derivatives, directional derivatives, etc. One more type is that when we have a function from some set to Rm, means Euclidean space, not just R1 but to Rm. So in that case, we say it as a multi-valued function. Why we say it as a multi-valued function? The reason is that for any x belonging to the domain, the image point fx is in Rm, and therefore it has components, means first component up to m component because it is in Rm. So we can write for any x belonging to the domain, we can write the image point fx as having components y1 up to ym, where yi's are what? They are some real numbers, means each y1 up to ym, each y is a real number. That is how we can write. And this coins out the concept of component functions, because for every x belonging to the domain, fx is having m components as real components. So in that case, for this type of function from s to rm, means multi-valued function, we can have a concept of component functions. Now these component functions will be what? They will be real valued functions and having same domain which f was having. So how many component functions will be there? Whatever the dimension of this codomain space Rm is. So the dimension of Rm is m. Therefore, number of component functions will be m. So f1 to fm. So naturally, how they will be? So for any x belonging to the domain, fx will be what? Fx will be the first image, first component of the image point. Similar way, f2 will be second image of the second component of the image point. Same way, the last component function fm will be defined from same domain set to R. How it will be? Its fx image will be the last component. Fm will give mth component ym. So that is how we can create real valued functions from multi-valued functions, and these real valued functions are called component functions. And now let us discuss the most general form. Means, okay, let us go back. Means, in the multivariate functions, we had only one independent variable and multiple dependent variables. And in the previous case, means when it was multivariate function, when domain had multiple variables, so there were multiple independent variables, single dependent variable. And here in multi-valued function, we had single independent variable and multiple dependent variables. Now let us consider the most general case. In that case, what will be happening? There will be multiple independent variables and multiple dependent variables. So the function in its most general sense will be a function from a subset of a Euclidean space Rn to another Euclidean space Rm. They may be same also, in particular m may be equal to n, so we can have that case also. But let us consider the most general case in which f is a function from a subset of Rn to Rm. This is in general called function of several variables. So this type of function, in which when we consider a function of several variables, we are assuming that n and m both are more than one. Otherwise, this will be the simple most case, that f from R to R. This type of case it will be, which we have already discussed in our basic differentiation concepts. We already know that. There is one more specific name for that when we have n and m both more than one. So in that case, we say this function of several variable as multi-valued multivariate function. Multi-valued because of m greater than 1, and multivariate because of n greater than 1. So the above two concepts are together considered here, and therefore this is called multi-valued multivariate function. Now let us recall from the concept of linear algebra, because in this part of discussion of real analysis, we are already discussing about linear transformations also from Rn to Rm. So let us consider what a linear transformation from Rn to Rm is. Definitely it's a function. So it's a function from Rn to Rm. So it's also a function of several variables like this. So if we consider f from Rn to Rm a function, so in fact linear transformation is also a function from Rn to Rm. So in this concept, we can have a function of several variables, in particular a linear transformation also. And what this linear transformation is, therefore, it's a function of several variables, means from Rn to Rm, having what speciality? It satisfies linearity on addition and scalar multiplication. Means if we have x plus y, where x and y are in Rn, then this linear transformation distributes over it. A of x plus y gives you ax plus ay. Similar way, it distributes over scalar multiplication also. Means if we have x in Rn and a c, some scalar in as r in r real number, then a applied to cx will be as c into ax. So ax will be here. So that is how already we have discussed one functions of several variables, which in linear algebra called linear transformation. Now we are proceeding one step more towards the differentiation of functions of several variables. For that, we have to understand that most general sense, means if we have a function from a subset E of Rn to Rm, in that a function of several variables like this, means a Venn diagram I have made like this for understanding. Let us understand first the behavior, means the properties of the domain, the universal set of domain and codomain. What they are vector spaces. So Rn or Rm also, it's a vector space over R, and it's a metric space also. Means Rm is a metric space with respect to its metric, and Rm will be metric space with respect to its own metric. So we have similar metrics for each. Both are called Euclidean metric in their spaces. And therefore this vector space, which is a matrix space also, this is a non-linear space. That means we have as in our previous videos we have already discussed that Rn is a non-linear space over R. Similar way, Rm is also a non-linear space over R. And we have already discussed in our videos that when we write norm of some element in Rn, say x, so we can write just like simple bar x means straight bar. It's like this in single bar. And same way we can write single bar for elements here also. But they have their own meaning. We also know it from our previous discussions. Now we are discussing for this function of several variables, which is in general sense, not particularly linear transformation. We are having some function of several variables from E, where E is subset of Rn, to codomain Rm. We are considering this. I'll first discuss a few basic things, and then we will go to the definition when we will be prepared for that. So let us see that for any given x belonging to the domain E and corresponding some neighborhood point y in E again. So when we say y and x are in E, so they are in Rn also, which is a non-linear space as we discussed. So what will be the difference? The difference will be all in also in Rn by the vector space property. So it will be in Rn. So x and y are in Rn because they are in E. Therefore, their difference is also in Rn. See, x and y are in E, but I can't say their difference is also in E. For that, I have to satisfy algebraic properties, etc. I am not assuming that E is also satisfying those properties or something like that. We are simply assuming that x and y are such points such that they are in E, but definitely whatever they be, their difference means y minus x will be a vector in Rn. So that is how we can write it. And thus we can take the norm of that also. It is defined in that sense. And now let us see, means as x and y are in domain, so their images will be where? They will be in codomain, which is Rm. Therefore, their difference because will be in Rm because Rm is also a vector space. So their difference as vectors will be in Rm. Now, 2 points means x and y in subset of Rn. If I want to find out the distance between them through Euclidean metric, through Euclidean distance, so definitely we can find out the distance from of y from x. It will be in terms of norm. I can write norm of y minus x. We are particularly writing this in terms of norm because our all discussion goes on for the vector spaces and metric spaces which are norm-linear spaces. So Rn and Rm we consider them as norm-linear space. So here this distance is nothing but difference of y and x and their norm taken. So that is the distance between y and x, and the distance between the image points fx and fy will be what? It will be again similar way norm of fy minus fx. That is how we can have it. So means it's just an inspiration to understand if we in particular had y and x in R and the function be f from R to R, the most basic concept we have we generally discuss for differentiation. So what we discuss is means as y tends to x, fy means the difference of fy minus fx is the difference between them, the change in fy and fx per unit change in y and x. So when we try to find out that, that becomes the rate of change of this y as it comes closer and closer to x, and then we obtain like that, and we get the corresponding concept of differentiation of function f at point x. So a similar thing is being done here, but in terms of distance. There also distance between x and y will be in terms of real numbers. There, if this sign is for absolute value of two real numbers, then also we discuss like this. And if these fx and fy are real numbers, then also we use this symbol for corresponding thing. But here, this is not the absolute value of real numbers. It's a norm of two points of Euclidean spaces. So that is how similar things are being used. That is the main motive to get the inspiration from our original definition, the most fundamental definition of function f from R to R. So means we are discussing like that. So I'll just change similar things, some things for notation. So whatever it is means y is a point here and in some neighborhood of x. So when we find out y minus x, this is h. So it's a vector. So y minus x is a vector. So I can write this vector as h. In that case, I can forget y, and everything I can write in terms of x and h. So what will be y? If y minus x is h, then y will be x plus h. And therefore, this fy also can be replaced with f of x plus h. And therefore these norms and distances etc can be written, means distance between y and x therefore will become what, y minus x, means where what is y, x plus h, so it will be norm of h. And similar way, distance of fy and fx will be what, it will be f of what is y, x plus h, f of x plus h minus fx, norm of that. So that will be their distance. We are going to use this because we will consider in terms of differentiation at point x, means differentiation of function f at point x in terms of some neighboring point y with the distance norm h, such that this y remains in E, and that is what the motive is. Therefore the h and its norm, which is distance of the neighboring point y from x, is important, and that will play the role in difference in the discussion of definition. All right, let us club this diagram again and with the definition, which I have written in the previous slide also. So we'll discuss it along with the observation from this diagram. No, okay. So what is the definition for a function? It's when we say that a function f from E to Rm, where E is a open subset of Rn, it to be differentiable at a point x in its domain point E. I'll discuss it here, but let me tell you what is the motive of considering this set domain set E to be open subset. The only reason is that whenever we will discuss about fx, means a point x here, and fx plus h. So x plus h means neighboring point y, which is x plus h, such that when this h will tend to 0, means 0 vector, its norm, means norm will tend to 0. So norm of h will tend to 0, so that x plus h, means this y, will be very very neighboring point to it, and it is assumed that some radius will exist such that within that radius all the points in the sphere, open sphere of center x, will lie within the set E. That should happen, then only we will be able to consider f applied to x plus h. Otherwise f cannot be defined on this domain point if it is not in domain. If x plus h comes out of the domain, we will not be able to apply f to that function. So to make the f function applied to the neighboring point, we need this to be open set, because open set says that we have for this x considered as center, there exists a radius with which there will be open spheres subset of this open set. So that is what the property of open set, the definition of open set, playing role here to make this f of x plus h meaningful. That is what this need is. And now let us exactly understand what this function of means this function f at this point to be differentiable means. We say that this function f is differentiable at this point x if and only if there exists a linear transformation. Means at a point x the functions will be differentiable if there exists a linear transformation from where, from Rn to Rm, linear transformation A from Rn to Rm. It looks very vague, but the definition how it goes on means please be with me. I'll just make you understand what it is going to be. So what we say, a function f is differentiable at point x if there exists a linear transformation from Rn to Rm. What is Rn here? It's a superset of the universal set of the domain set, means E was domain of function f, so its universal set is Rn. From this Rn to its codomain Rm, there should exist a linear transformation such that this full expression is satisfied. In that case, if this expression is satisfied, in that case we will say that function f is differentiable at this point x. So it's a very vague looking definition, but it has similarity if you see from here, as I have discussed in my previous slide, that when we discuss about distance between fy and fx and distance of y and x. In terms of that, if you look for it, so it's norm of f of x plus h minus fx norm of h. When you see in denominator, it is like similar concept like that only. So what we are saying is that this, and in that case what will happen, we will say that the derivative of the function at this point x, which we generally write it as f dash x, will be this linear transformation. So it's amazing concept here that if we have functions of several variables from a open subset of Rn to Rm. In that case, at a point in the domain, a function is differentiable if and only if there exists a linear transformation satisfying this condition, and in that case, the derivative at that point x is that linear transformation itself. And what this in that case, what we say this derivative as, we say this derivative as total derivative of f at x. So this is the notion behind it. So we can use that just like we say functions, f function from r to r. In that simply we say derivative. If we have from Rn to r, in that case we say partial derivatives. But here what we will say, we will because it's from Rn to Rm or a subset of Rn to Rm, in that case the derivative will be called total derivative. So that's all behind, but let us now complete the definition part with this understanding of limit. Means function f is differentiable at point x if and only if there exists a linear transformation such that this limit is 0. What is that limit? See, it is very similar concept looking like with what we discussed originally for derivatives and partial derivatives. Limit of, see, what is the change from x to x plus h. So what is the distance? It's norm h. When we move from x to x plus h, this y is x plus h. So what is the distance covered? It is from x to x plus h. The vector is h. So the distance is the difference of the initial point and end point, that's norm h. So distance of in the domain points, the difference between the domain points and the distance of codomain points, that is fx plus h and fx, so difference between them. So what we are doing is here simply making a little modification. We are not simply putting norm of x plus h minus f x and dividing by norm h. Here we consider inside the norm itself what we consider the linear transformation which we have considered that should exist for the differentiability of this function. This linear transformation applied to this vector h. See, what is this linear transformation? This linear transformation is from Rn to Rm. And what is h? H is in Rn. So that means this A as a linear transformation applied to x. We can put a bracket here, braces here. So A braces inside H. So that is what is done. But because we are having so many braces, this, and we specifically want to say that this is the function we are discussing, and just to make the distinguish between just to distinguish between the function and linear transformation, we are not putting here this one. In fact, there is one more motive behind not putting this braces, is that linear transformation is a concept which is very close to matrices. So somewhere at some places we consider some matrices multiplied with that, equivalently a linear transformation applied to some vector in Rn. So with that inspiration also we can omit the bracket, and therefore what we have is limit as h, the vector h tends to 0. That means the distance between an x and x plus h is tending to 0. So effectively we are saying that these the points y, or y means x plus h, these are in very near points of x. They are neighboring points of x. So for those neighboring points of x coming from any side, what happens that when this distance between them tends to 0, the norm of f of the image point of the neighboring point minus the image point of the original point x minus this a applied to this distance function h, means distance h, the norm of that divided by norm of h should be equal to 0. So that is what, if it is satisfied for some particular linear transformation from Rn to Rm, in that case we say f is differentiable at x and its derivative is this linear transformation itself. So that's all about the definition. But let us observe one more thing from here, from this definition itself. See, if this x is fixed, and if f function is differentiable at this x. So what we have this there exists a linear transformation A satisfying this condition, and then we say that f dash x is it's this linear transformation. But now let me change this x from here to here. So if I have changed x, so if the derivative of f is differentiable at this x also, means derivative exists, so that means what? A linear transformation again exists. And we can never say that the same linear transformation A for the first x and the same linear transformation for the second x is same. We can't say like that. So means when we fixed x, for that this linear transformation existed, and we said that this derivative is this linear transformation. So we will have to say for a new x, a new linear transformation. That means if if I have some x star here, new point. So if f is differentiable at x star, in that case, what I will say that there exists a new linear transformation, say a star or b from again. This will be same domain and codomain. A star from Rn to Rm, such that means this condition satisfied at x star here, and here will be what? A star. So this will be satisfied, and again we will say that derivative of f at x star is a star. So what happens this here is how many number of points in the domain are wherever the function f is differentiable, that many linear transformation correspond to their derivatives. So corresponding to each derivative of the function of several variables at a point x, there corresponds some linear transformations. So that is all about the fundamental and basic definition of differentiability of a function of several variables. So that is how we discussed about this topic. One more observation is one more result is there in this topic, that if function f is differentiable at x, this derivative a means derivative of f at x, which is we are saying a linear transformation a, it is unique. Means f dash x cannot be two linear transformation, a also and b also. So there will be unique linear transformation if the derivative exists. It will be derivative of that a unique linear transformation. We'll cover that proof in our next video, and there will be one more basic useful remark behind that, which will be useful for further discussions for derivatives of functions of several variables and their matrix representations also, which we'll be covering in our subsequent videos.